So this is our second lecture in thermal radiation heat transfer between surfaces. Last time we had the view factor. That was one of the most important equations, although we don't use it regularly. We just understand it and know how to compute it as needed, but often they're tabulated or they're more obvious to calculate. But the calculation of the view factor from surface I to surface J is 1 over the area of surface I, the double area integral of the cosine of that polar angle over surface I, cosine of that polar angle, surface J. Those polar angles are defined by the straight line between the two parts of the surface, and you'll have divided by that distance r squared of that straight line segment. You integrate over surface J as well as integrate over surface I. We also had view factor relationships. These we use more frequently than the definition of the view factor. The view factor relationship would be something like the summation rule, which would be the sum of the view factors for surface I, thinking about photons leaving that surface. They're going to be in an enclosure. If you sum over all the J surfaces in an enclosure, that has to equal the 100%. And then the reciprocity rule. So how well they transfer photons back and forth. If I can see you, you can see me. So it's AIFI to J equal to AJFJ back to I. When do the view factors Fij equal Fji? When the areas are equal. When the areas AI is equal to AJ. And last time we introduced the black body radiation exchange, and so that's where I'll pick up here today. So think of an enclosure. I'll call surface 1, surface 2, and then surface 3, something like that. And so those are the intersections of those surfaces. So surface 1, surface 2, surface 3. You characterize the temperature at surface 1, the temperature at surface 2, the temperature at surface 3. If they're different temperatures, there's going to be some exchange in this non-participating medium. You can think of a vacuum or just air in between in that enclosure. But if the temperature 1 goes up, what really drives the flow isn't the temperature, but it's the EB for 1. What is EB? The black body emissive flux. And that's sigma T1 to the 4th from Stefan-Boltzmann's law. And that's what drives the flow. So we model the flow as having a network where we'll have a node, and a node. Instead of temperatures at the nodes, we have the black body emissive flux at each of the nodes, EB1, EB2, and EB3. So each one of these, just as a reminder, sigma T3 to the 4th or sigma T4 to the 4th. And what do we have that would allow the flow of radiant energy back between these two surfaces? Some resistances. And what were those radiative resistances? They were the geometrical, RGEOM is what I like to call them, geometrical radiative resistances, 1 over AF. So if you're going from surface 1 to surface 3, it's 1 over area 1, view factor 1 to 3. Or you could put 1 over area 3, view factor 3 back to 1, either way. But in general, it's always the same form, the geometrical radiative resistance 1 over AF. Strongly encourage that you think about putting all the Q's into the network. So Q1 into the network, Q2 into the network, Q3 into the network. That's 3, and then this is 2. And then some of those Q's will probably be negative and some will be positive. If surface 1 is hot, then Q1 is probably positive to keep it hot, higher temperature than the surrounding temperatures. And if surface 3 is, let's say, cold, lower temperature, it's going to be probably a negative. This will probably be a negative Q3 because it's heat is having to be removed to keep it cold. to keep it cooler than the surrounding temperatures. And to develop the equations, you typically do an energy balance around a node. So the energy balance for each node, well, let's do it for node EB1. What we would have is we'd have the in, and then it's traditional to write everything else is flowing out. So the rate of heat transfer in Q1 is balanced by what flows out. I'll just kind of sketch it this way. Through the resistor 1 to 2, plus what flows out through the resistor 1 to 3. Why don't we write everything coming in? You could. You could do that, but I'm just trying to follow the textbook, and I think it's a good strategy. So it'd be EB1 minus EB2 divided by the resistance. 1 over A1 F1 to 2 plus what flows from EB1 to EB3 divided by 1 over A1 F1 to 3. And there's a good balance equation. You can write similar balance equation for each of those nodes. I recommend Q's in and then the flows away from that node through the resistors. Let's solve a problem. So we have a hemispherical dome. So you can think of half a sphere, and it covers a 25-meter diameter ice rink. So think of a ice rink that's located right in the middle of it, and the hemispherical dome is a larger diameter than the ice rink. Both the ice rink, which is made of ice, and the dome can be treated as black bodies. And the dome is at a temperature of 10 degrees C, and the ice is at -5. So organizing results or information, what we'll do is we'll call this surface 1. What's that? The interior, the roof of the hemispherical dome. And we could talk about the diameter of 1 is 45 meters. And the temperature of 1 problem is 10 degrees C. Might as well convert that right away to 283 Kelvin. It's a radiative exchange. We need those Kelvin, absolute temperatures. And then the other surface is surface 2. And the diameter of that rink at 2 is 25 meters. And the temperature at 2 is -5 degrees C, which is 268 Kelvin. Okay. You're interested in calculating the net rate of radiative transfer from the dome to the rink. Well, you could enclose and make a third surface here, the surface 3, to make an enclosure. You don't need to answer part A, but you could. Now that I have an enclosure, I can model a radiative network, but really it's just the interest. What you're interested in is the net rate of radiative transfer in the dome from 1 to 2, from the dome to the rink. So what you're going to do is you're going to calculate Q1 to 2 is simply EB1 minus EB2. Isn't 1 higher temperature? 2 is lower temperature. Divided by 1 over A1 F1 to 2, or even just put the parenthesis here and put the A1 F1 to 2 there and dispense with that 1 over them. So we have to make some area and view factor calculations. What's the difference if somebody said, I think I'd rather do area 2 view factor 2 to 1 and then multiply it by EB1 minus EB2? Will that give me the same answer? Sure. And what looks different, but you already know, why is that? Why are they the same? Reciprocity. Reciprocity, that's right. So which form? Both of them have EB1 minus EB2, and those are that's pretty easy to calculate, sigma t to the 4th, and we know the temperatures. Which one would you rather calculate? Would you rather use A2 F2 to 1, or would you rather use A1 F1 to 2? 2 to 1. Okay. Why would you want 2 to 1? It's a flat disk, and it's every photon leaving that flat disk is going to hit the enclosing hemispherical dome. So it's the view factor 2 to 1 is 1 by inspection or calculation. So, okay, what we need to do is, let me do this. Let me calculate the area 1 and the area 2. Okay. What exactly is the area of half of a dome, half of a sphere, that hemisphere? So you remember the area of the whole sphere is 4 pi r squared, which is pi d squared. Is that the area of a whole sphere? So what's the area of half of it? 1/2 pi d squared. So that's the d1, the diameter of the hemisphere. All right. How about the area of the rink? It's a circular rink. So it's pi r2 squared, pi r squared, or 1/4 pi d2 squared. True? All right, so we stick in our numbers, and sometimes it's good to do that and just take a look at the relative magnitudes. 3180.86 meters squared. Area 2 is 490.87 meters squared. There you go. All right. Well, if I put in my numbers for area 2 right here, 490.87 meters squared, put in the view factor 1, put in the Stefan-Boltzmann constant, 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th, multiply by the temperature of the dome 1, 283 to the 4th, minus the temperature of the rink, 268 to the 4th, and now both of those are Kelvin to the 4th, so I take the unit outside. I cancel the Kelvin to the 4th, I cancel the meter squared, and we calculate a Q, which is the net rate of radiative transfer from the dome to the rink, is 34.9 kilowatts. That's the answer to part A. How about the answer to part B? What is the view factor from the dome to the rink? What are they asking you to calculate for part B? F1 to 2. True? And you're just going to use reciprocity. Is the answer for the view factor 1 to 2, is it equal to the view factor 2 to 1, area 2 divided by area 1 from reciprocity? And we already know what view factor 2 to 1 is, 100%. And we calculated the two areas. That's why one of the reasons I wanted to calculate them. And then we get the view factor 1 to 2 is equal to 0.154. Does that seem low or high or what? Seems pretty low, doesn't it? Seems pretty low. Let's continue this problem. So the problem is continued, and the question is simply find all of the view factors. Well, I have 3 surfaces to make the enclosure. So we have the hemisphere, we have the cooler ice, then we have this surrounding area. So our numbering is 1, 2, and 3. What does the area of surface 3 look like? Like a ring, yeah, right. So it's flat though. Okay, so if you wanted to calculate all the view factors for a 3-surface enclosure, it would be the view factor 1 to 1, view factor 1 to 2, view factor 1 to 3, the view factor 2 to 1, view factor 2 to 2, view factor 2 to 3, view factor 3 to 1, view factor 3 to 2, view factor 3 to 3. How many things? 9. And often when you look at it, some of them you can observe to be 0, equal to 0. How many of these are equal to 0 for this? Okay, 2 to 3 is equal to 0. 3 to 3 is equal to 0. 3 to 2 is 0, and 2 to 2 is 0. Is there anything else that's 0? Okay, then sometimes some of them are 100%. That's right. This is 100%, this 100%. You can make that by the observation that the flat surface 2 is just going to go up into the hemisphere. Or you can even just say summation rule and summation rule once I find out the other ones are zeros. Okay? Summation rule with respect to surface 2, forces 2 to 1 is equal to 1. Now, we just calculated the view factor for the 1 to 2, was it not? Wasn't this view factor 0.1543? How would I calculate 1 to 1 or 1 to 3? Which one do you want to tackle? Probably 1 to 3, and the recipe or the strategy would be? The reciprocity. Again, reciprocity. So you do A1 F 1 to 3 is equal to A3 F 3 back to 1. And we know 3 back to 1 is 100%. So we get to the area of the view factor 1 to 3 is the area ratio A3 over A1 view factor 3 to 1. I already calculated the area of surface 1 and 2. The area for 3 is going to be the pi over 4 d of the outer surface, which is d1 squared minus d2 squared. That area for surface 3 comes in at 1099.56 meters squared, and I'm not going to just repeat the values from the previous slide, but when you put in the it's D1, yeah, D1 and D3 are the outer, yeah. And so then we get the view factor, let me just write it up here. The view factor from 1 to 3 is 0.3457. One last view factor. How would you calculate view factor 1 to 1? They have to sum up to 1. Use summation rule. And when you do that, you find it's 0.5000. That's good to 4 significant digits. What do you think the 5th significant digit would be? Another O. Something special about half of a hemisphere. Or, I'm sorry, half of a sphere, which is a hemisphere. Half of the photons are going to hit on whatever's below it or the floor of the hemisphere. Okay, so look good. Half of the challenge doing black body radiation calculations, getting the view factors. Let's solve another problem. We have a long L-shaped metal part that's hot. It's 1,000 Kelvin. It's cooled radiatively, so there's no convection cooling. It's just radiatively being cooled by somehow suspending it in a long 1.5 meter diameter semicircular duct. So the semicircular duct, what would it look like? Something like this, maybe. Like this? True? And we have this part. It's an L-shaped part. I don't know. Put it like this. That's the L-shaped part. Okay. And that L-shaped part's hot, and the duct, semicircular duct is cool. They give you the diameter here of this semicircular duct. Let's the D is equal to 1.5 meters. The metal part is very thin, so it's thin, and it has 0.1 meter length on each side. So what is the distance from here to here? Let's call it W is equal to 0.1 meter. And from here to here, W is 0.1 meter. So W is 0.1 meter. Okay. Both the metal part and the duct surface can be treated as a black body. True? And left off the question part, but it's what you asked to find is Q. What is Q? Is the rate of heat transfer from the hot part to the cooler duct, enclosing semicircular duct, per length of the hot part. So we're looking for Q prime or Q per unit length into the third dimension of that part. How are we going to solve it? How would we solve it? Well, let me do this. I need to clean up a little room in here. I know the dimensions of the L-shaped part. Let me ask you this question. Does it matter if the part's oriented this way, or that way, or that way, or that way in the duct, or this way in the duct? I mean, does it matter? No, it doesn't. It doesn't. Okay, so any which way we put it is fine. Now, I want to have as few surfaces as possible. How is the radiant energy from the hot part going to get to the duct? You can think of how many parts of the surface are there for this L-shaped. There's really 4 to take into account. Kind of 2 on the outside and 2 on the inside. Now the photons on the outside, they will go with what type of view factor to the duct? Will they somehow hit the metal part itself, or will it be 100% leaving that surface and going to the duct? So what I would do is I would say I'm going to model leaving the outer surface of the L-shaped metal part, and then I'm going to model the rate of heat transfer from the interior 2 surfaces, and then I'm going to sum them up to get the net rate of transfer. So I'm going to do it this way. What we're going to do is we're going to say this is surface 1. This is surface 2, and all of that is surface 3. Make sense? And so to get the total rate from the hot metal part, I'm going to get Q 1 to 3 divided by L plus Q 1 to 2, 2 to 3, not 1 to 2 to 3 divided by L. It's what's coming off the outer edges plus what comes off the inner edges. Which of these 2 parts is going to be easier, the first or the second part? The first. Yeah, let's go ahead and write it out. What would that be? So the Q 1 to 3 per unit length would be what? Well, it's both of them are black bodies. And so it's going to be the EB1 minus the EB3. And then instead of dividing by the 1 over AF, let's just put it A times F. Okay, so the A times F would be the area 1 view factor 1 to 3. All right, let's finish the calculation for this one. So we'd say, what is our area for the L-shaped outside of the L-shaped part? 2 W's, right? 2 W's. We would multiply by L, but we already divided over by L, so that's over there in the right part of the equation. The view factor from 1 to 3 is 100%. And now we have the Stefan-Boltzmann constant. We're going to have the temperature of that part 1 to the 4th power minus the temperature of the cooler walls, let's say 3 to the 4th power. We have all the pieces, don't we? And so let me just put some numbers in here. 2 times 0.1 is the thickness, right? Yeah, 0.1 meter times 1. 5.67 times 10 to the minus 8th watts per meter squared, Kelvin to the 4th. Then we're going to have 1,000 to the 4 minus 300 to the 4, and I pull the units outside, Kelvin to the 4th. Cancel, cancel, cancel one of the meters, and we get watts per meter. And we can run that number, and we find that 11.25 kilowatts per meter. That's what's going from the outer surface of the metal part to the wall. Let me ask. I'm going to make a calculation for this term right here. Do I think it should be greater than 11.25, equal to 11.25, or less than 11.25? Less. Why? It's either because when I do that calculation, let me show you the equation, Q 2 to 3 per unit length is equal to area 2 view factor 2 to 3 times EB2 minus EB3. Is there any difference in the potential which drives a radiative? The black body emissive fluxes are the same. Is there any difference in the area of 2? No. The difference comes into play because of the view factor. True? The view factor is less. It's lower. So how do I calculate the view factor from 2 to 3? Maybe I concentrate on my metal part for a little bit, and I come up here and the part looks like this, and this is W length, and I make a nice enclosure. And that's the same as 3. Now I have a triangle. We worked it out last time, did we not? But we worked it out where it was the view factor from 1 to 2 was 1 minus the sine of alpha over 2. Right? And so it's depending on how you want to do it, the view factor, you have to work out the view factor, okay? The view factor from all of this surface here to that surface. You could use reciprocity, you could use a number of different things. Let me do this. Get rid of calling it surface 1 there and just call this 2. 2 has, I'm getting, get rid of alpha. 2 is this plus that. Does that make sense? 2 is the whole interior shape. Let's use reciprocity. The area of 2 times the view factor from 2 to 3 is equal to the area 3 view factor 3 back to 1. Okay, how does that help me? I'm trying to calculate the view factor 2 to 3. Am I not? So the view factor 2 to 3.
Maybe 3 to 2. Is that correct?
Well, this is 2 right here, this interior part, and this is 3. I just enclose it. I make a little enclosure. I don't have any surface 1 anymore. I got rid of that. Oh, that's where you're saying. Thank you. Very good. Thank you. All right, so this is going to be the area of 3 divided by the area of 2 times the view factor 3 back to 2. What is the area of 3? Hypotenuse. If each edge is WW, what's the hypotenuse of the right triangle? Is it the square root of 2 times W? Look good? All right. So we put in the area 3 square root of 2 times W divided by 2W for the area of 2. And what is the view factor from 3 back to 2? 1. So what is this view factor from 2 to 3? 0.7071. Square root of 2 over 2. Does that look reasonable? All right, that was a lot of work. But that's the only real difference, because we then come back to this equation and put in that view factor. And let me just summarize down here that the Q from 2 to 3, the interior surface of that L-shaped metal part, is 0.7071 or 70.71% of what it was for the outside because of the view factor. And so it comes in at 7.95 kilowatts per meter. So the total per unit length is 19.2 kilowatts per meter. All right, let's press forward then. Now we want to summarize if we had a general enclosure. Let me try and draw it for 4 surfaces. And all of the enclosure surfaces were black bodies. So put a surface like this, 1, 2, 3, 4. They don't have to be flat surfaces. They can be some curved surfaces. So we have surface 1, 2, 3, and 4. How would we model it? Well, we would introduce a radiative network. What would be the nodes of that network? The EB1, the EB2, the EB3, the EB4. Oops, 4. Can write 4 now. And how are they connected? What's the resistance between them? 1 over AFs. Did I put in, if I stop right there, did I put in all the resistors? No, there's a resistor between 1 and 3. And between 2 and 4. Now did I get them all? There can be a lot of radiative resistors if you have a lot of surfaces in the network. Okay. And then recommend that you put Q into each of those nodes, knowing that if some of them are positive, then some of them are going to be negative. And then what would you write? You would write a balance equation for every one of these nodes. Let's just pick one to write a balance equation for. Let's do it for 4. You want to do it for node 4? So the balance equation, what do I mean by balance? Energy balance equation, right? The energy balance equation for node 4 would be Q4 is in, and then always model going away through the resistors. So the sum of the outs would be EB4 minus EB3 divided by 1 over A4 view factor 4 to 3 plus EB4 minus EB2 divided by 1 over area 4 view factor 4 to 2 plus EB4 minus EB1 divided by 1 over area 4 view factor 4 to 1. Did I write it correctly? So you can get a bunch of equations depending on what's unknown for your problem. Maybe you know some of the temperatures, maybe you don't know some of the other temperatures, maybe you know some of the Q's, maybe you don't. It's mix and match. It depends on the problem. But you have to solve it. Okay. Well, what do we do now? Well, what we're going to do is we're going to take and modify this now for a gray surface. So to start with the gray surface, I'm going to copy this. Edit, copy, come over here, and I'm going to do a paste. So let's say we have the exact same 4 surface enclosure, but they're gray surfaces. What's the difference between a black surface and a gray surface? The emissivity. For a black surface, the emissivity is 1. What is it for a gray? Less than 1. And so you think, oh, now I'm going to have an emissivity over here. Emissivity surface 1, emissivity surface 2, emissivity surface 3, and emissivity surface 4. That's the difference. How does it modify? How do we modify our network? Well, let me kind of just do this. You push back the node for the EB surfaces. The EB nodes are pushed back. And you have a radiosity node for each surface now. And you have an additional resistor. Remember this 1 over AF was a geometrical resistance? Now you have a surface resistance. A surface resistance which is 1 minus emissivity divided by the emissivity area. I'm going to drive that. But before I drive it, I want to show you what's the change, what's different between the black body enclosure, a radiative network, and gray surfaces in the enclosure. So the Q would be dumped in here. How would you change this node? Same thing. You push back, put in additional resistor from EB2 to J2, and then this is Q2 coming into the network. Similarly, modify here. So we'll push this back. This is now the J3 node. This is the EB3 node. That's Q3. And each one of these additional resistors are the surface. 1 minus the epsilon, the emissivity of surface 3, divided by the emissivity of surface 3 times the area of surface 3. 1 minus epsilon over epsilon A. Let me go ahead and finish it. And so that's J4, EB4, and this is Q4. Somebody says, how is EB1 related to the surface temperature of 1? Is it still sigma T1 to the 4th? It is. Yeah, it's still the black body emissive flux given by the Stefan-Boltzmann law. What about J1? How about J2? How about J3? What is the name of J again? I can't remember. J is called the radiosity. Okay, it's the radiosity. It's some measure of net outgoing radiative flux from a surface. How am I going to calculate it? Is there an easy way to relate it back to a temperature of surface 1? Not really. It's more complicated now, isn't it? And often you have to solve for the whole network to get the J values. Let me ask this question. What are the SI units of the EB1 and EB, all of them? What are the typical SI units for the EBs? Watts per meter squared. What are the typical SI units for the J's? Watts per meter squared. So it's not watts, but it's watts per meter squared. What are the typical SI units for these Q's? Watts. What are the typical SI units for the geometrical resistances 1 over AF? Dimensionless, meter squared, 1 over meter squared? Yeah, it's very interesting. 1 over meter squared. How about the SI units for the surface resistance 1 minus epsilon over epsilon A? What are the typical SI units? 1 over meter squared. Isn't it? Because what's the emissivity? Units in emissivity? Dimensionless. Dimensionless. So now you could do the same thing. You could say, well, I have a bunch of nodes. I can write an energy balance. Let's do it for this node right here. Can I write an energy balance for that node? What would it look like? Well, I have Q1 coming in, and I only have 1 out going through that resistor. What would that balance equation look like? EB1 minus J1 divided by 1 minus epsilon 1 over epsilon 1 A1. Okay, let's do a more challenging node. Let's do this node, just like we did before. But instead of it being the EB4 node, it's the J4 node. What would that energy balance look like for that node? Would it be, well, do this if you want to. You can write it a number of different ways. A lot of times it's writing in this network going out away from a node. You could write it going out away from a node, or you could write it going into the node. But as I've sketched the assumed direction, we would say nothing in and all 4 going out. You're going to have a J4 minus an EB4 divided by 1 minus epsilon over epsilon A plus J4 minus J3 divided by 1 over AF, which maybe I should put the subscripts there because it's A4, F4 to 3, plus J4 minus J2 divided by 1 over A4 view factor 4 to 2, plus J4 minus J1 divided by 1 over A4 view factor 4:1. Did I do that correctly? You see once you get the pattern, it's pretty straightforward, I hope? Okay. Let's go ahead and derive that 1 minus epsilon over epsilon A. The derivation it's probably one of the more detailed calculations or difficult things in this chapter. It's not that hard. So think about a surface right here, and I have some incoming irradiation, incoming flux, G. What happens to the G? Two things can happen to the G. Part of it can be absorbed into the surface. That's alpha G. What happens to the other part? Rho G. What do you call rho G? It's the reflected part, isn't it? Then we also have emission from a gray surface. What would be the emission? It would be the emissivity times EB. Then we also have Q coming in from the other, let's say, conduction or heat source below. Well, now we're ready to do an energy balance and do the energy balance for that surface. If you do the energy balance for the surface, what do we have? We have the flux equal to, that's an incoming still, and alpha G is incoming, equal to emissivity EB. So the two ends to the surface equal the one out, which is emission. Couple things. Should this be a double prime on that Q or not? Yet it really needs to be a double prime on that Q. All right. All right. Another question I get a lot, where's the rho? Where's the rho G in this equation? Well, it didn't it didn't come into the surface. It bounced off. So the only thing that comes in for a real energy transfer to that surface is alpha times G. What's alpha? Absorptivity. All right. Now, let's get to another equation. This other equation is the definition of J. What is J defined as? J is equal to rho G plus emissivity EB. Does that make sense? Okay. At this point, you want to employ and say that both of these equations are going to be modified assuming a gray surface. A gray surface. All right, what does it mean to be a gray surface? What's the relationship between absorptivity and emissivity for a gray surface? They're equal. And this is an opaque surface, so the reflectivity is 1 minus the absorptivity. And if the absorptivity is equal to the emissivity, then the reflectivity is 1 minus epsilon. So our heat flux, what you could do, like if you want to get rid of that Q double prime, put Q divided by area. You can do that or do it later. Let's do it later. Is it plus the emissivity times G equal to the emissivity EB. How about this equation? Well, it's J equal to 1 minus the emissivity G plus emissivity EB. Now what I want to do is I want to take this equation and express G in terms of everything else. So G is J minus E sub EB divided by 1 minus epsilon. Is the algebra okay? Once I've isolated G, take that G and use it, maybe get rid of that line there, substitute it, so eliminate G out of both of those equations. If you eliminate G out of both of those equations, you get Q double prime equal to, let me throw it on this other side, minus the epsilon times G, which is J minus epsilon EB divided by 1 minus epsilon plus This was a minus, right? Plus epsilon EB. Did that look okay? All right. If I multiply and divide by 1 minus epsilon for that second term, I get everything Q double prime is, everything's over 1 minus epsilon. So I can look to see if I can cancel some terms. And so we're going to get minus the emissivity J plus the emissivity squared EB plus emissivity EB minus emissivity squared EB, in which terms cancel. Those two cancel, true? And so you have the Q double prime is equal to the EB minus J times epsilon over 1 minus epsilon, or 1 minus epsilon, you put the epsilon there. And Q double prime was Q divided by area. So Q, what we wanted to get, the equation for Q is equal to EB minus J divided by 1 minus epsilon over epsilon A. And now we do some name calling, and we call that term our radiative surface resistance. What drives the flow through it, the difference between the EB and the J, the black body emissive flux and the radiosity. That's the derivation. Hopefully it made sense. Let's jump back to this. I could have an enclosure where some surfaces are gray with the emissivity, let's say 0.5, and 1 or 2 surfaces are black. What happens to the surface if emissivity 1 goes to 1? What happens if surface 1 becomes black? What happens to the network? What about this resistor, this surface resistor, if emissivity 1 is 1? It goes to 0. So think about your electrical analog. If I have no resistance, what is the difference in the voltage? 0. It collapses. So in that case, this would collapse to 0. Then these two nodes would become one node, and EB1 is exactly the same as J1. All right? All right. So you can take a gray surface network, and then if one surface becomes black, you can see how it collapses and gets rid of the J node. Well, with that, I'm done for today. We'll pick up there next time. Thank you for your attention.